So now we're going to look at electron energy levels, and I strongly suggest this is a section not to read in your textbook. Your textbook kind of goes more in depth and less in depth in different areas, so I really recommend that you don't read your textbook. Just kind of look at the pictures. Treat that section as a picture book. I would also advise against looking up things on the internet. This concept, this electron energy levels, this stems from quantum mechanics. So you may have heard of quantum theory, quantum mechanics before. It's basically some intense, crazy math. So just be aware if you do an internet search, you may get over your head very quickly. So hopefully if you need some more clarification, by all means, send me a message, send me an email, text, or post a forum, and maybe some of your other classmates could also add in some of their knowledge of the area. So to kind of look at where we are in terms of our understanding of our atoms. Okay, we're thinking basically of Rutherford's atom, okay, tiny, dense, positively charged nucleus, and then we have our electrons going around. Remember, we originally were thinking of this as the planetary model, so that the electrons basically just rotate around and around and around that nucleus. But what happens is, if we go to try and locate and pinpoint where those electrons are located, what exactly is that orbital or that orbit that they're taking? And what happens is, if we pinpoint that location, we change the nature of the electron. Okay, so if we're trying to learn about something and we find it and we go to study it then once we found it and its characteristics have changed, then there's no point in looking at those characteristics. Okay? If the characteristics that we're able to see then are different than what those characteristics were originally, then we didn't learn anything new. Okay? So what they determined is, basically, instead of pinpointing this location, we're going to look at it more of on the basis of a probability factor. Okay, what is the probability, what is the likelihood that we're going to find the electron in this area? Okay. So this probability that we get, okay, this comes from quantum mechanics, quantum theory. It's basically the same thing, works interchangeably. I put in here basically, aka quantum mechanics. Basically, it's intense, crazy math. Okay, quantum mechanics is actually why I fell in love with chemistry. So if you'd like to see some of this intense, crazy math, I could show you. We could talk about it. But for most of you, just by hearing the word quantum or math, most of you probably cringed your nose a little bit at that. So we're not going to look at the math. We are going to look at just the basics of what quantum mechanics tells us. Okay, to kind of understand more this concept of where these electrons are located. And I've put this location in quotation marks because really it's not a location, it's just a probability of finding the electron in a certain area. Okay. So we can locate or describe this location by the combination of 3 different variables. Okay. Really there's 4, but for us we're just going to talk about 3. Okay. And again, remember, this is a very, very brief overview, a brief look into where these electrons are. Our first concept, our first variable that we can describe the electron as, is called the energy level. We can also, sometimes this is referred to as the quantum level. And we give this a symbol because it is math for us. Basically a symbol of a lowercase n. And your book has this little cartoon. We have our energy level here, our energy increasing, and basically it says you can think of these energy levels like bookshelves. Okay, so this first one down low, this would be n equals 1. Second would be n equals 2, n equals 3, equals 4, and n equals 5. And we can have as many energy levels as we want. Okay, n can go to infinity. It has no limit. Okay, and basically what happens is our electrons are going to kind of live in these different energy levels. Okay, it can't live in between, but it can live in those energy levels. And in general, what we're looking at is the higher n values basically mean that we are further from the nucleus. So n equals 3 is further away from the nucleus than the n equals 1 level. Okay. So that's our energy level. Our shape, or we call this our orbital. Okay, you can think of it kind of as the pathway, but this is where the math comes in. This is the probability. Okay, where can we find that electron? And we have 4 different shapes of orbitals. We have the s orbital, we have the p orbital, the d orbital, and the f orbital. I'm going to leave myself enough room here, but we'll make do. So the s orbital, and this has the shape of a sphere, and usually we just represent it as a circle. The p orbital, this is called usually a dumbbell shape or a figure 8 shape. And so we have that. We have our an example of an s orbital down here, just a sphere. The shading kind of involves or suggests that it's 3-dimensional. This here is an example of a p orbital, that dumbbell shape. Our nucleus would be in the center here. Again, nucleus and the s orbital would be in the center. The d orbitals, we have a double dumbbell. So we're looking at something like that. And it kind of looks like a fan. Your book also gives you an image of those. There are 4 that have that shape. And then we have a 5th shape that's kind of a dumbbell plus a donut. That one kind of looks like a p orbital, but then it has this donut that kind of goes around. Okay, again, check your book out. I'm no artist, and you can look at that. Our f orbitals, these are really, most of them are going to look like a double dumbbell. Okay, try saying that 10 times fast. Basically, I'm going to put this down as it's complicated. You can do a Google search, do a f orbital, and you know, look at what some of those are look like. For us, it's not important. Really, we're just looking at this in a very general way. So that is our second way of describing our electrons. Okay, is what shape is that orbital? Okay, so instead of having just a circular orbit, we have these orbitals. They are in 3 dimensions. And basically the electron can be anywhere inside that orbital. It doesn't have to stay on that path. Okay, it can be found anywhere in that shape. The third way that we can describe where the electron is located is this concept of which orbital is it. Okay, and this is the 3D orientation. So I'm going to switch pens. So I'm basically doing number 3 in the blue. Okay. For the s orbital, we have a sphere. A sphere only has one orientation. Okay, if we have, say, a sphere, hopefully you can kind of see my hands. If we want to rotate that around in space, it still takes on the same shape. And nothing's changed. So for an s orbital, we only have one. So only one kind of this, we call this orientation. For our p orbitals, we're going to have 3 orientations. And those orientations are represented down below here. This is an image taken from your book. This is, we have the px orientation, so those lobes, we call these lobes, on the dumbbell are on the x-axis. We have a py, those lobes are along the y-axis, and pz. So those are three-dimensional orientations. So if we, what happens is on the atom, these are all crammed together. Okay, they're all, our nucleus is in the center. So we have the px, we have the py, and we have the pz. Okay, maybe that's worth me putting into colors. So there's the px. It didn't really give me a different color. Well, I tried. What can I say? My pens may have failed me this time. If I do that one a little bolder, we can at least see that there are 3 there maybe now. So those are the 3 orientations that we can have for our p orbitals. For your d orbitals, again, you can consult your book, but there are 5 different orientations. 4 of them involve the double dumbbell shape, and then only 1 has the dumbbell plus the donut shape. Okay. And then again, the f orbitals, they're complicated. Just trust me, there are 7 3-dimensional orientations for them. Now, we're talking about electrons, right? So our electrons can be so far from the nucleus, okay, that's our energy level. So the higher the energy level, the further away they are from the nucleus. They have different shapes that they can be found in. And each of the shapes has a certain amount of orientations in 3 dimensions that they can have. Excuse me. So if we look at kind of, this is another figure from your book, comparing our s orbitals. Okay, this number out in front here, this 3, that's representing our quantum level, our energy level. Okay, so this is an s orbital, and it's in the energy level of n equals 3, so we call it a 3s orbital. And this number here, we have n equals 2, and then n equals 1. And notice that they get bigger and bigger as your quantum number increases. Okay? So that's what I mean when I say the higher the n, the further away from the nucleus that electron is. Okay? Or where it can be found. So that's kind of what we can think of very simply. Okay? Now, each one of these orbitals, okay, each one of them can hold or can house, can have living in there, okay, 2 electrons. So each orbital can have 2 electrons. So what that means is our s orbitals can have 2 electrons. So that's our s orbital. I really didn't leave myself enough room here. Our p orbitals can have 6. Our d orbitals can have 10. And our f orbitals can have 14. So if you've ever taken chemistry before, or if you have this whole 2, 8, 18 kind of numbers in your head, that's where those are coming from. Now, before we walk away from from this lecture, I just want to show you, kind of explain to you what the implications of these numbers are. Okay. And I want to also take you back to when we talked about the periodic table, and I said, some of you are thinking logically, well, hey, why can't we just cram all of the elements in a nice, neat, square table, have all the same number of columns, same rows, and it'll be nice and pretty. And I said the shape of the periodic table is very intentional. The shape itself tells us a lot of information. Okay. That's why I included this image here. Okay. And this is kind of our periodic table, and it's broken apart just a little bit. Okay. Period numbers shown. Over here we have this is hydrogen. Helium normally lives over here. They've brought it over here so because it belongs over here when we look at it this way. But remember, so these are s orbitals. Okay, our electrons live those outermost ones, the furthest ones from the nucleus are in s orbitals. Okay, and there are only 2 electrons that can live there. Okay, so that's why we have 2 spaces here. We have the group 1A and the group 2A. Then we'll ignore the D block for now. Going over to our P block. Right, this is groups 3A, 4A, 5A, 6A through 8A, and these are our p orbitals. We can have 6 electrons. 1, 2, 3, 4, 5, 6. Oh, maybe coming clear. Okay, and our d orbitals, we can have 10 electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then our lanthanide and actinide series, which is pulled down below, have our f orbitals. There's 14 electrons. You can count for yourself, but there are 14 elements listed across there. Okay. So really cool how the periodic table, the shape of it, tells us where those electrons are found, how far away from the nucleus they are, which is actually going to correspond to their period numbers. We can say the shape, which depends on which column they're in, which group they're in. Okay, 1A and 2A are in s orbitals, that outermost electron. And we can look at the 3D orientation, and each of those 3D orientations can have 2 electrons there. So periodic table, very, very, very powerful tool, even though when you look at it, you may have thought it was fairly simple.